Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at the concept of rational numbers. And let us quickly recall what we did the last time. So last time we defined what a relation is. A relation on a set X is merely just a subset of X cross X. This is a piece of notation that instead of writing this, we write this. And now there were these bunch of concepts about reflexivity, irreflexivity, symmetry, antisymmetry, and transitivity. I've written the definitions here. You can pause the video and look at them. We then discussed the notion of posets as an illustration for the notion of relations. But this concept will be useful even later. So a poset is merely a pair where the first part of the pair is a set and the second part is a relation with the properties that it is reflexive, antisymmetric, and transitive. So this is a device which allows you to compare things in the set P, just like we can compare things on natural numbers. The only difference is that you may not be able to compare everything. So for instance, if we take the Boolean poset that we did, the power set poset that we discussed the last time, you can't, for each, if you choose two different subsets of a set X, it's not necessary that one is contained in the other. So it's not necessary that one can compare any two elements in a poset. So that's that. More about that in the next line. But before that, a piece of notation which I did not discuss the last time was that if suppose we have a poset and we have this situation, meaning the first guy is smaller than the second guy and they are distinct, then we write this, just like in natural numbers. So this is consistent with what we have been doing with this symbol for the rest of our lives. Okay. And now another definition that I did not get into last time is basically that of a totally ordered set. So a totally ordered set is a partially ordered set with the property that where you can compare any two elements. So whenever we are given two elements in this partially ordered set, either the first one is smaller than the second one, or the second one is smaller than the first one. So if this happens, then we call it a totally ordered set. An example of a totally ordered set is the natural numbers with the usual ordering. An example of a poset which is not totally ordered is the power set poset, which was considered the last time. So take this as an exercise and show that this is not totally ordered. Basically, you need to find two elements of the power set such that none of them is contained in the other. And that's of course very easy. All right. And then we discussed the notion of an equivalence relation. An equivalence relation is a relation on R which is reflexive, symmetric, and transitive. It's a very important class of relations. We saw that the equivalence classes of an equivalence relation partition the parent set. The equivalence classes are defined this way: basically the collection of all elements of X which are related to a given element. That is the equivalence class of the given element. The set of all the equivalence classes is denoted by this symbol, and we noted that this is a partition of the set X. And lastly, we discussed dictionary between the set of all the partitions of a set X and the set of all the equivalence relations on the set X. And that's where we ended the previous lecture. And now let us continue. Before that, of course, we have these three problems that I urge you to pause the video and solve them. And now let us get to the notion of rational numbers. So we are all familiar with the rational numbers, but the point of this lecture is to construct rational numbers out of integers. So we saw that we started with natural numbers with the well ordering principle, and now from there we saw that we can construct integers, and then now we are going to construct rational numbers out of integers. So we are not going to take them for granted, we'll construct them. And the construction is of course a little bit technical, but I hope that one will be able to see the point of this construction, that it is not the rational numbers are not God given. It's as we say, God only created the natural numbers, everything else is the work of man. The rational numbers are also the work of man, but we need to reconcile whatever construction we are going to give with our usual understanding of the rational numbers. So that is very important. Alright, so with that, let us get into the details. So we need to somehow talk about these fractions. Alright, so here is how we do it. So consider So recall that z is the set of all the integers. Okay, and now consider all the pairs. So let's say maybe the set S be defined as all the pairs a comma b, where a is an integer and b is an integer, but b is non-zero. So it's just a collection of such pairs, and we will define an equivalence relation on it. So define a relation tilde on S as follows. So we will write a comma b tilde x comma y if and only if the product of ay equals bx. So this looks weird, but what are we trying to do? We are trying to think of this as a fraction. So instead of looking at this way, just think of it like this and think of it like that. And when do we say that these two rational numbers are equal? We say that they are equal precisely when this cross multiplication gives you this. So that is why we are defining this relation. That's the motivation for it. Okay, and let's check that this is an equivalence relation. For reflexivity, a comma b tilde a comma b. This is simply because ab equals ab. So reflexivity is fine. Symmetry is also clear because once you have this equation, you just write it in the reverse order and you get that. So a comma b tilde x comma y gives us, by definition, ay equals bx, which gives us bx, or maybe I should write xb, that would be better. Let's see. Ay, yeah, let's write xb equals ya, which implies x y tilde ab. Right, so that's that, and transitivity I'll leave you to check. Exercise. Okay, so we get an equivalence relation, and the rational numbers will be equivalence classes. So define Q. Q is this set which is S mod tilde. So this is the definition of rational numbers, and of course this looks very, very strange, and we have to say something about this. So first a bit of notation. The equivalence class of a comma b will be denoted by a slash b or a over b, and we see where is this going. This is how we write rational numbers, as a quote-unquote fraction. Okay, so when are two things equivalent? We already said, we already defined it this way, and you see this is an equivalence class. When is this equal to when is this equal to another equivalence class? And that happens precisely when AD equals BC, or CB if you want to write it that way. So that's exactly what happens in our usual rational numbers. Okay, so we have a set. Now we want to define addition and multiplication on it, because rational numbers can be added and multiplied, so we want to mimic that also. So define A by B, this equivalence class, plus C by D as AD plus BC by BD. Okay, so this plus is something that we are defining. This is a recipe to define sum of two rational numbers or two elements of this thing. Now there is already a problem here, because when we define anything by equivalence classes, we need to see that it is actually well defined, because if we choose a different representative of the same equivalence class, then we need to check that the right hand side is indeed the same thing. So what we need to check is that if A prime by B prime equals A by B, and C prime by D prime equals C by D, then AD plus BC upon BD equals A prime D prime plus B prime C prime B prime D prime. This is a routine check, but let me emphasize why we need to do this. Because this is not a single element. This is a collection of elements of this thing. So if somebody chooses a different, A prime comma B prime, such that this is in the same equivalence class as A comma B, then that guy would get something else written here. He would see A prime B prime instead of what we see right now. So for this to even make sense, that thing that we get should be equal to what is written here. So one has to check this, and this I leave as an exercise, because this is a routine check. Just play around with the definitions. So this is, and hence the addition is well defined, and hence plus is well defined. And same story for multiplication. Define A by B, C by D as AC by BD, and again check well definedness. Which is exactly what we did here. That's the kind of thing that we need to do. So we will need to check that A prime C prime upon B prime D prime is equal to AC upon BD whenever A by B is equal to A prime by B prime and C by D equals C prime by D prime. This is what you need to do. Okay, so that one needs to do. And then further properties is distributivity and commutativity, etc. So let me add a page. So here are for a bunch of exercises. Show that A by B plus 0 by 1 equals A by B. Again, for all A and B, where B is non-zero, etc. Show that A by B plus C by D equals C by D plus A by B, just as we expect. A by B, C by D is C by D, A by B. And what else? Yeah, so very important, A by B. What should I write? X by Y plus, we are running out of symbols, P by Q equals AX. Basically this distributes. That's that, and yeah, maybe one more thing. So X by Y, Y by X equals 1 by 1 if x and y are non-zero. So yeah, so these are a bunch of things which, of course, we've been doing this since childhood. These are familiar operations of rational numbers. So we have constructed rational numbers. The point is that we have constructed them rather than, somebody just told us how to write fractions that are number here, and a slash here, and just out of nowhere such things coming up. No, we can construct them. Okay. Further, lastly, we need to talk about ordering. So we note that every element of the rational numbers can be written as A by B, where B is positive. Why is that? Because suppose what we have is something like, let's say, 2 by minus 3. So my claim is that this is nothing but minus 2 by 3. And this is not much of a claim, you just cross multiply and you get it. So basically, whenever you see a negative in the denominator, you can just push it up. So you can write everything in this fashion where the denominator is positive. And now we declare. So this is another relation that we're defining on rational numbers. So we declare A by B less than equal to C by D, where B and D are positive natural numbers. B and D are natural numbers if AD is less than equal to BC. So this use of less than equal to is coming from the natural numbers. Two natural numbers can be compared. While this is something that we are defining and we are using the same symbol for it, that may get confusing, but just bear with me. There's a good reason why we can use the same symbol, and we have been using the same symbol for all our lives, so it's not nothing new. Okay, so this is how we define this relation, and one can check that this is the total order. Check that. Is a total order on Q. Okay, so that's it. And now we need to talk about how we identify natural numbers sitting inside rational numbers, because we always think of natural numbers as particular kind of rational numbers. Right now what we have done so far is just that we constructed something out of the set of integers. Okay, so it's not right now clear that how one can think of integers as rational numbers in a consistent way, in a useful way. So that's the point of this. So not just natural numbers, we of course want to identify all the integers with integers inside the thing we just defined, rational numbers. So here is how we do it. Okay, I will do it in a somewhat technical way, but I hope you get the point. So define a map phi from Z to Q as phi of anything, let's say M, equals M over 1. So this is how we define it, and this map allows us to think of every integer as a rational number. So once you're given an integer, you put a slash in here. So this equivalence class is now thought of as the integer that we started with, and one sees that phi is injective. So that's one thing. So at least this is not losing any information on the set theoretic basis, meaning it does not take two different integers and sends it to the same thing. So that's good. And further, it respects the algebra of Z, meaning phi of M plus N is phi M plus phi N. Phi of M times N is phi M phi N. and it also respects ordering. So m is less than equal to n if and only if phi m less than equal to phi n. Again, this is something that was there for integers, while this is for rational numbers. So under this map, now one can think of integers as rational numbers. So now when we write m, we can think of it either as m over 1 and think of it as a rational number, or we just can think of it as an integer. And now we will not put a fine print on this point. Now we'll be treating these things just like we did in high school. So when we write m, we may, without any qualification, think of it as a rational number whenever we want, and without any qualification, we may think as an integer, and we will not make mention of this map phi every time. In fact, this is the last time we are mentioning it. So the whole point of this exercise is that rational numbers can be built out of integers in a synthetic way. We'll not use this construction again, but it is important to at least see it once in one's life. Okay, so that's that. Right, so in the next lecture we'll talk about fields, because we want to say that rational numbers form a field, and then we want to define real numbers as a certain kind of field. Okay, so this is all that I wanted to say today. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.